Okay, so I wanted to give you a little bit of a refresher about how we predict double replacement reactions and also how we write something called a net ionic equation. So the general format for double replacement reactions involves two compounds reacting to form two new compounds. So the general format that's followed in these particular situations is like an AB plus CD giving you an AD plus a BC. So if you look at the example that I have here, we have sodium chloride, which is aqueous, reacting with silver nitrate. And if we remember that the two metal ions are just going to swap places, we can predict the products, and the products would be silver chloride, which the charge of silver ion is +1, and the charge of the chloride ion is -1, so the chemical formula is AgCl. And then the other product would just be sodium nitrate, NaNO3. Now, that's just a prediction. We always have to check to see if the reaction actually happens through the formation of a pure solid, a pure liquid, or a gas. Now, typically what you'll see with these types of problems are pure solids forming. We call those precipitates. And to determine the answer, we're going to use something called a solubility table. So the key thing I want you to pay attention to is if you look at your two products, like silver chloride here, we'll find silver. Notice it's right here in the column. And then you're going to go down to chloride. Notice it says insoluble. So that tells me that silver chloride is a precipitate. So we can denote that with the solid. And let's just double check the other piece here. So we look at sodium nitrate. So go over to sodium, go down to nitrate, and notice it says it's soluble. So in that case we would put AQ. So this reaction will occur because we see the formation of a solid. In this case, our precipitate would be silver chloride. Something that's important to remember, and especially when we start to look at net ionic equations, is the reason why we represent things the way that we do. So remember that ionic and covalent compounds behave differently in solution. And what's important to remember here is that with an ionic compound, it dissociates. It forms discrete ions. So in the case of sodium chloride, these would be sodium ions that were positive and chloride ions that were negative. And we call these types of solutions electrolyte solutions. And we call them electrolytes because they conduct electricity. Covalent compounds don't do that. What covalent compounds do is they dissociate into dissolved molecules. So instead of forming ions like ionic compounds, they'll just form discrete molecules. And the example here is sugar, which is the same one that we talked about in class. And we call those non-electrolytes because they don't conduct electricity. An interesting thing to note that we didn't bring up in class that's good to think about is, well, does that just mean that all ionic compounds will always conduct electricity? And the answer is no. If you look here, we have three examples. So we've got example A, which is just water. You can see water right here with the oxygen and two hydrogens. Pure water, just like what we saw in class, does not conduct electricity. Now if we take that and change the situation and take like table salt, something that we know is an electrolyte, in the solid state, it doesn't conduct electricity. And the key thing to remember here is there are no mobile ions. You have to have mobile ions in order to be an electrolyte. So if we actually melted the salt, then it would start to conduct electricity again. Or we could just dissolve it, which is what you see here in example C. And the only reason why it's conducting electricity is because, look, we've got these mobile ions here, these negative ions and positive ions that can move throughout this solution. So what this really means is when we write an overall equation, which we're used to seeing something like this, we're really not being true to what's in the solution. So we write something called a net ionic equation to simplify things and really show what changes. Because if you think about it, with this equation, we have sodium ions and chloride ions in solution. We don't really have NaCl. We have sodium ions and discrete chloride ions. And likewise, we have silver ions and we have nitrate ions, because anything that's aqueous is going to dissociate if it's ionic. and both of those are ionic. And that also means that on the product side we'll have sodium ions and nitrate ions, again because it's aqueous. Okay? But over here, silver chloride, that's the species that actually stays together. It does not dissolve. So I'm going to write it in a different color for clarity. That's our precipitate, our solid. So when we write net ionic equations, all we really have to show are those things that change. And by change, I mean change state. So change from, in this case, aqueous into our precipitate. And if you get rid of everything else, and these things that don't really change here, we call those spectator ions. We can eliminate those and then just write the equation that you see here in red, where we have silver ion plus chloride ion giving us silver chloride. And if we represent this kind of on a quasi-nanoscale, if we had silver ions as like these little silver spheres and chloride ions as these green spheres forming a precipitate where they're bound together, you would see that in solution we would have the precipitate down at the bottom. Notice we have several units there, and then floating around in solution would be the spectator ions that didn't really change much at all. So when you're asked to write a net ionic equation, just remember to show the ions that are involved in forming the pure solid, the pure liquid, or the gas. That's it for tonight.